Hello, young math enthusiast. Today we shall talk about the concept of partial derivatives. Partial derivatives is a process applicable to functions with more than one independent variable. Say for example, if we have the dependent variable z expressed as a function of two independent variables, let's say x and y. So let's say z is equal to 2x squared y minus xy cubed. So this is a function with more than one independent variable. So we can apply the process of anti-differentiation or finding the not differentiation, finding the derivative of z with respect to one of the independent variables at a time. That is why we call it partial derivative. Partial because we shall find the derivative of z with respect to only one of the independent variables at a time. By the way, the symbol for partial derivatives could either be of these symbols. It could be f sub x of xy, that is if z is expressed as the function f with the independent variables x and y. So z here is f of xy. Then the derivative would be written as f sub the variable wherein we derive it from. Let's say we derive it with respect to x, so that would be f sub x of xy. Or it could be this symbol here, partial derivative of z with respect to x, that is if we derive it with respect to x, or partial derivative of z with respect to y, whatever the case may be. Or it could also be written as z sub x, meaning we derive z with respect to x. Or if we derive it with respect to y, we write z sub y. Or it could also be written as the partial derivative of f with respect to x. Or in the case wherein we derive it with respect to y, so we write the partial derivative of f with respect to y. Okay, now for the definition, how do we define formally the concept of partial derivatives? So we have here the definition. Let z be a function of x and y. So f of xy, and let this be a function of two independent variables, namely x and y. Let all indicated limits exist. So we have two limits here enumerated. Then the partial derivative of f with respect to x is defined as f sub x of xy is written also as the partial derivative of f with respect to x as the limit of f of x plus h y minus f of xy all over h as h approaches 0. While the partial derivative of f with respect to y is written as f sub y of xy, or the partial derivative of f with respect to y, as the limit of f of x y plus h minus f of xy all over h as h approaches 0. So if one of these limits do not exist, then we say that the partial derivative do not exist. Say for example, Let us take for example, suppose z is expressed as let's say 6x y squared, and we are trying to look for the partial derivative of z with respect to, let's say, x. So by definition, this is the limit of, so suppose this is f of xy, so that is by definition f of x plus h comma y minus f of xy all over h as h approaches 0. So we substitute x here by x plus h and y by simply y for the first value of the function f. So we'll have the limit of, so we have 6 times the quantity x plus h. That would be, this is, we replace x by x plus h. Then we have y squared. So that is, this is our f of x plus hy minus f of xy would just be 6x y squared all over h as h approaches 0. So this will then be equal to the limit of, this will give us, simplify this, we have 6x y squared, then 6hy squared, so plus 6hy squared, okay, minus 6xy squared over h as h approaches 0. So this will then be equal to 6xy squared minus 6xy squared is 0. So we'll just have the limit of 6hy squared over h as h approaches 0. But then, since h rather approaches 0, it is not equal to 0. Meaning, h over h should be equal to 1. Therefore, we shall have the limit of 6y squared as h approaches 0. So, solving this limit, we'll just have 6y squared. Okay. Now, if we would look at the original function and the result that we obtain, we see that the partial derivative therefore with respect to x of the expression 6x y squared was found to be 6y squared. Okay. Now, recall that suppose we have to find the derivative of, let's just say 6x with respect to x by the derivative theorems. This will just be evaluated as 6 Okay? Meaning, what will be left will just be the constant. If we would look here, so we see that when we have derived the expression, what were left were 6 and y squared, meaning y squared therefore was treated as a constant, the same as we treat x. Okay, we can actually derive that. We can actually find that out by applying it to other examples. That is, if we are trying to derive with respect to x, we would treat all other variables other than x as constant. So if we therefore are to derive, let's say, if we derive this same expression, 6x y squared, with respect to y this time, since we are deriving with respect to y, then we treat x as a constant, meaning that will just be the same as deriving, let's say, just for analogy, if we are to derive, let's say, 6y squared ordinary derivative with respect to y, rather, this is y. Erase that. We are to derive that with respect to y. The answer would then be 12y. Meaning, here, we simply multiply the exponent to the coefficient, then subtract the exponent by 1. So we do the same here. We multiply the exponent to the constant with coefficient, but this time, x is included as the constant, the coefficient of y squared. So we'll have then 12x, that is 6x times 2, then y, then subtract the exponent of y by 1, so that will just be y to the 1, or simply 12x y. Okay, I hope you got that. So let us take another example. Hence, following that, following that process, if we therefore are to derive or find the derivative, the partial derivative of, let's say, 2x cubed y squared minus 5x squared y plus 7xy, but let us derive this with respect to x first. Okay, so there is a theorem that the derivative of a sum or difference is the same as the sum or the difference of derivatives. Meaning, if we are to find the derivative of this expression, we derive each term one by one. So, here, since we are deriving with respect to x, y will be held constant. So, the derivative of the first term, therefore, will be 6x squared y squared. Again, that is since y squared was held constant, the same as 2 in this term. Then, minus, so again, we derive this with respect to x. Y will be held constant. So, we'll just have 10x y. And then here, y will be held constant, the same as we treat 7. So, the derivative will just be 7. But if we derive this same expression, 2x cubed y squared minus 5x squared y plus 7xy with respect to y. So here, x this time, all the x terms will be held constant. So the derivative of this expression with respect to y will then be 4. X cubed will be held constant. Then y. How do we get that? We multiply the exponent of y to the coefficient 2. Then subtract them the exponent by 1. The same is true with the second term with respect to y. So 5x squared here is the constant. So the derivative will just be 5x squared plus the derivative of 7xy with respect to y will be 7x. Okay? And we express that as the informal definition of partial derivatives. The partial derivative of f with respect to x is the derivative of f obtained by treating x as a variable and y as a constant. So that is with respect to x. The partial derivative of f with respect to y is the derivative of f obtained by treating y as a variable and x as a constant. Okay? So I hope you have understood that one. Now, the concept of partial derivatives also has the concept of derivatives of higher order, meaning we can also compute second partial derivative, third partial derivatives, and so on. So we have here the definition for a function z expressed as f of xy. If the indicated partial derivatives exists, then the partial derivative of the partial derivative of z with respect to x written as this symbol. This is now the second derivative of z with respect to x is f of xx of xy, which is f z sub xx. Take note that the same notation is used in finding the second derivative of the same function with respect to the other pairs of variables, pairs of x and y. But then take note that if f here is continuous, then the second derivative of z with respect to yx will just be the same as the second derivative of z with respect to xy. Let us have an example. Let us go back to the example that we had earlier. Okay, so note that the partial derivative of this expression with respect to x is 1. Hence, if we take the partial derivative, the second partial derivative of the same expression, 2x cubed y squared minus 5x squared y plus 7xy. Let's say with respect to x. By definition, we can have this written as the partial derivative with respect to x of the derivative of this expression with respect to x, the first partial derivative. So that is, we found that as 6x squared y squared minus 10xy plus 7. So we simply repeat the process of finding the partial derivative. So this will just be equal to, so we derive with respect to x, So y squared is held constant. So the answer would then be 12xy squared for the first term. Second term, 10y will be constant. So we'll have minus 10y. Then the derivative of a constant with respect to x is just 0. So this will therefore be the second partial derivative of the expression, this one, with respect to x. Next, if we are to find the partial derivative of the same expression, 2x cubed y squared minus 5x squared y plus 7xy with respect to x, then with respect to y. Meaning, this will be the partial derivative with respect to y of the partial derivative with respect to x. So, we can then write this is the partial derivative with respect to y of the partial derivative of the expression with respect to x. So, we recall that the partial derivative is 6x squared y squared minus 10xy plus 7. So, deriving this time with respect to y, so x will be held constant, will then have 12x squared y minus, this time x is held constant, so we'll have 10x plus 0, or simply 12x squared y minus 10x. Okay, now let us take the partial derivative of the same expression with respect to y, then derive it, or find the higher order derivative for such derivative with respect to y. So, this time, if suppose we would like to know or to solve for the partial derivative the second partial derivative of what expression was that again? Two x cubed y squared, 2x cubed y squared minus 5x squared y plus 7xy plus 7xy. This time with respect to y. So by definition, this will just be the partial derivative of, with respect to y, of the partial derivative of that expression with respect to y. So derive this in with respect to y first. So we'll have x cubed will be held constant. So we'll have 4x cubed y minus x squared will be held constant. So that would be 5x squared plus 7x. So this is the first partial derivative of this expression with respect to y. Then derive that again with respect to y. So again, x cubed will be still held constant. So we'll just have 4x cubed. Then there are no y here. So all of these are constants, meaning the derivative will all be 0. Okay. Next, suppose we would like to find the derivative this time, the second partial derivative of the same expression 2x cubed y squared minus 5x squared y plus 7xy with respect to y and then with respect to x. So this will be, I'm sorry, this is not the division. This will then be the partial derivative with respect to x of the partial derivative of this expression with respect to y first. So again, first partial derivative of this expression with respect to y was found earlier as 4x cubed y squared y minus 5x squared plus 7x. Then derive this time with respect to x. So y will be held constant. So we'll then have 12x squared y minus, with respect to x, the derivative is just 10x. The derivative of 7x will just be 7. So this is now, again, the second partial derivative of that given expression with respect to y and then later with respect to x. Okay, so I hope that you now understand the concept of partial derivatives. You can now work on your learning guides and then work on your learning tasks later. That would be all for now. Thank you for listening. Bye-bye.